Welcome to lecture series in physics. In this lecture series, we are discussing the topic or we are discussing the subject Introduction to Nanotechnology. So, while discussing this paper Introduction on Nanotechnology, it is necessary to explain some of the concepts pertaining to solid state physics. So far, we have seen what is a crystal structure and how a crystal structure differ from amorphous solid and what are the Bravis lattices, 14 Bravis lattices, and how to draw these Bravis lattices in 2 dimension and 3 dimension. In this episode, we are going to discuss about face centered cubic nanoparticles and what are tetrahedrally bonded semiconductor structures and what are lattice vibrations and we will be discussing about energy bands. So, under this energy bands, we will be having a thorough knowledge on insulators, semiconductors and conductors and what is reciprocal space and how to differentiate energy bands and gaps in semiconductors and what are effective masses and Fermi surfaces. So, let us now turn our attention to face centered cubic nanoparticles. So, when you take the metals for example, all the metals are in the solid state and when the metals are in the solid state, they form a lattice known as closed packed lattice. So, some of the metals are silver, aluminum, gold, cobalt, copper, platinum and lead and as well as the rare gases like neon, argon and xenon are face centered cubic structures. So, what are face centered cubic structures? Examples of face centered cubic structures are silver, aluminum, silver, aluminum, cobalt and copper are face centered metal atoms and all the rare gases like neon, argon and xenon are face centered cubic structures and magnesium and zinc are hexagonally closed packed structures. So, we have two kinds of structures here. One is a face centered structure, another is hexagonally closed packed structures and magnesium and zinc comes under hexagonally closed packed structures. Therefore, a number of other metallic atoms crystallizes in the not so close packly body centered cubic lattice and a few such as chromium, lithium and strontium crystallizes in all three structure types depending on the temperature. Therefore, an atom in each of the two closed packed lattice has 12 nearest neighbors. So, when you look at this diagram, this is the face centered cubic unit cell and there are 12 neighbor atoms that surround the atom. So, this darkened circle at the center it surrounds the atom with the neighbor atoms and this is the 13 atom nanoparticle in a face centered cubic structure unit cell. So, this looks like a polyhedron and the nanoclusters are associated with it. So, if another layer of 42 atoms is laid down around the 13 atom nanoparticle, so one obtains a 55 atom nanoparticle. So, that is when you add this 42 and 13, it becomes a 52 atom nanoparticle and the shape of this 55 atom is known as decatahedron shape and larger nanoparticle with the same polyhedral shape are obtained by adding more layers and the sequence of numbers in the resulting particles where n is equal to it is 1.13 it goes on which are listed in the table are called structural magic numbers. So, for n layers, the number of atoms capital N in this FCC nanoparticles is given by the formula. Therefore, the magic numbers that we have been discussing are called structural magic numbers, and these magic numbers arises from minimum volume and maximum density nanoparticles that approximate a spherical shape, and you have a closed packed structures characteristics of a bulk solid. The other important point is, when speaking on magic numbers, these magic numbers does not take any account of the constituent atoms of the electronic structure, and therefore, sometimes the dominant factor in determining the minimum energy structure of small nanoparticles is the interaction of the valency electrons of the constituent atoms with an averaged molecular potential, so that the electrons occupy orbital levels associated with this potential. And also the other important point to remember is atomic cluster configuration in which these electrons fill closed shells are especially stable and constitute electronic magic numbers. Their atomic structures differ from the FCC arrangement. The type and type 2,6 binary semiconducting compounds crystallize with one atom situated on a FCC sublattice, and for a FCC sublattice displaced from the first by the amount 1 by 4, 1 by 4, 1 by 4 along the body diagonal as shown in the figure. And such a kind of structure you call it as a zinc blende structure. And when you look up at the figure, when you look at this figure, that each zinc atom is centered in a tetrahedron of S atoms, so which are denoted by the black spheres. The S atoms are denoted by these are the black spheres. These black spheres are S atoms, and likewise each S has a 4 similarly situated zinc nearest neighbors. When you look at this diagram, so there are 4 situated zinc neighbors, 1, 2, 3 and 4 neighbors are there. The small sized dashed line cube delineates one such tetrahedron. The same structure would result if the zinc and sulfur atoms were interchanged. The elements silicon and germanium crystallize in the same structure by having the silicon or germanium atoms which occupies all the sites on the two sublattices. So, therefore, there are 8 identical atoms in the unit cell. In the unit cell, you have 8 identical atoms, and this arrangement is called the diamond structures. So, I have shown the different kinds of diamond structures. The first one is the unit cell of the diamond structures, which contains only one type of atom here. So, this is the first diamond structure which contains only one type of atom, and the corresponding unit cell of the zinc blende structure is B, which contains 2 atom types. So, this contains, the first figure contains one atom type, the second figure contains 2 atom types. Therefore, the rods here represents the tetrahedral bonds between the nearest atoms or nearest neighbor atoms. So, this is the nearest neighbor atom and this is the nearest neighbor atom. So, the rod here represents the tetrahedral bonds, and the small dashed lines delineates a tetrahedron as particle shown in the figure. Since the alkali halide and the alkaline earth chalcogenide compounds fit the ionic module so well, and it is significant that neither module or neither model fits the structures of the semiconductor compounds. The extent to which the semiconductor crystals exhibit ionic or covalent bonding is not clear from crystallographic data. So, let us describe the wave function by writing as psi is equal to, it is A covalent psi covalent plus A ionic plus psi ionic. Therefore, the coefficients of covalent and ionic wave functions here are normalized. So, when in this equation the covalent wave function and the covalent wave function and the ionic wave function are normalized. When these wave functions are normalized, you get a structure like this. And what are lattice vibrations? We have discussed atoms in a crystal as residing at particular lattice sites. Let us say some atoms in a crystal are residing at a particular lattice size. But in reality, what will happen is they undergo a continuous fluctuations in the neighborhood, and therefore, the regular positions of the lattice will be disturbed. And because of this fluctuation or this fluctuation arise from the heat or thermal energy in the lattice. When you supply thermal energy or when you dismantle the lattice, what will happen? The fluctuation arise from the heat and become more pronounced at higher temperatures. Since the atoms are bound together by chemical bonds, the movement of one atom about its site causes the neighboring atoms to respond to this motion. Therefore, what will happen? The chemical bond acts like spring that stretch forth and compress repeatedly during oscillatory motion. So, in the oscillatory motion, what will happen? This atom acts like springs. So, the chemical bonds that act like springs that stretch and compress repeatedly during oscillatory motion. So, due to this, what will happen? Many atoms will vibrate, and this vibration spread throughout the crystal. And due to this, every type of lattice has its own characteristic frequencies of vibration called normal modes. And the overall collective vibration motion of the lattice is a combination or superposition of many normal modes. So, let us take for an example a diatomic lattice such as gallium arsenide. In the gallium arsenide, there are low frequency modes, and these low frequency modes are known as acoustic modes. And in the acoustic modes, the light atoms tend to vibrate in phase with each other, and the frequency will be higher, and such a mode you call it as optical mode. And similarly, these atoms may also vibrate out of phase. Similarly, a simple mode for analyzing these vibratory modes is a linear chain of alternating atoms with a large mass and a small mass m joined to each other by spring. So, this is the spring type of arrangement shown in the diagram. This figure shows the dependence of K for the low frequency acoustic and the high frequency optical longitudinal modes. We see that the acoustic branch continually increases in frequency with the increasing wave number K, and also the optical branch continuously decreases in frequency. And the atomic vibrations that so far we have been discussing are corresponding to a type of wave known as standing wave. And this vibration motion can also produce a travelling waves, and these travelling waves can travel entirely through the lattice. So, the classical example of such travelling waves are sound moving throughout the air, or seismic waves that start at the epicenter of an earthquake. So, these waves travel thousands of miles to reach a detector that records the earthquake event many times, minutes or seconds later. So, therefore, localized travelling waves of atomic vibration in solids are called phonons. So, what are phonons? Phonons are the travelling waves, when the atoms in the solid vibrate, they produce known as phonons, and these phonons are quantized, and the energy of the phonon is given as h omega, that is equal to h nu, where nu is equal to omega by 2 pi, and omega is the frequency of vibration. And these phonons play a prominent role in the physics of a solid state. And the above figure shows the dependence of the longitudinal normal mode vibrational frequency of the wave number, where the wave number k is equal to 2 pi lambda for a linear diatomic chain of atoms. So, this shows the linear diatomic chain of atoms with the alternating masses capital M, and the equilibrium spacing you call it as sigma, and connected by a bonds the spring constant is C. Therefore, there are two modes, one is an acoustic mode, another is the optical mode. So, for the optical mode, the general equation is root of 2c plus 1 by m plus 1 by m, and the other equation also corresponds. We can approximate this to as an effective mass, that is 1 by m plus 1 by m as an effective mass of 1 by m, which turns out to be root 2c by m. And we will be discussing about the energy bands, about insulators, semiconductors and conductors, and what are reciprocal space lattice, and what are energy bonds and gaps of semiconductors, and what are effective masses, and what are Fermi surfaces. And this is the schematic band energy diagram for insulators, for semiconductors and for conductors. So, whether it is an insulator or a semiconductor or a conductor, there are two kinds of band, valency band and the conduction band. So, the valency band will be in the lowermost and the conduction band will be in the uppermost. So, between these two bands there is a gap, and this gap is known as the band gap, and this is the y axis represents the energy, and therefore, this is the valency band. For an insulator I am speaking. In the insulator, the electrons are all in the valency band, and there is a conduction band. Between this conduction band and valency band, the band gap is there. So, when you look up at this band gap of this insulator, it is a little bit large. So, the band gap for the insulator is very large, and when you reciprocate this band diagram to semiconductors, so you have the valency band, electrons are there in the valency band, and similarly in the conduction band, in insulators there are no electrons, but whereas in the semiconductors there are a small number of electrons in the conduction band, and when you look at this band gap, the band gap is very smaller in size. This is for semiconductors, and similarly for conductors, the valency band and conduction band overlap with each other, where in the valency band there are a handful of electrons, and in the conduction band there are number of electrons. So, what is the main difference between insulators, semiconductors and conductors depending on the band gap? For the insulators, the band gap is large. For a semiconductor, the band gap is small. For a conductor, the band gap is overlap or it is nil, we can say. So, when a solid is formed, the energy levels of the atom broaden and it forms bands with the forbidden gaps between them. Therefore, these electrons can have energy values that exist within one of the bands, but it will not have the energies corresponding to values in the gap between the bands. The lower energy bands, due to the inner atomic levels, are narrower or all of electrons. So, what will happen is they do not contribute to the electronic properties of the material, and these parameters are not shown in the figures. So, the outer or the valence electrons, the other name for valence electrons are outer electrons. These valence electrons bind the crystal together, occupy what is called a valency band. But when you take for an insulating material, the valency band is full of electrons and therefore it cannot move, and because they are in a fixed position in the chemical bonds. There are no delocalized electrons to carry a current, so the material is an insulator. Regarding speaking about the conduction band, the conduction band is far above the valency band in energy as shown in the figure. So, the conduction band is not thermally accessible and it remains essentially empty. In other words, we can say the heat content of the insulating material at room temperature is 300 Kelvin is not sufficient to raise an appreciable number of electrons from the valency band to the conduction band. So, the number in the conduction band is negligible. So, another way to express is to say that the value of the gap energy, and if Kb is a Boltzmann constant and if Eg exceeds Kbt, and this is the schematic diagram for the energy bands of an insulator. So, for A, this is the energy band of an insulator, and B, this is the energy band of an intrinsic semiconductor, and C, it is the energy band of a conductor. So, when you look all this diagram, there is a cross hatching is there. So, this cross hatching indicates the presence of electrons in the bands. So, you have electrons in the bands, here also you have electrons in the bands, here also you have the electrons in the bands. So, therefore, the density of electrons reaching the conduction band by this thermal excitation process is relatively low, but by no means it is negligible, because the electrical conductivity is very small. Since the electrical conductivity is very small, we term the material as semiconducting material. And what is an intrinsic semiconductor? If the electrical conductivity is very small and it behaves like a semiconducting property, and such a kind of material you call it as intrinsic semiconductor. And this semiconductor can be doped with donor atoms that give electrons to the conduction band, where they can current the current scenario. So, the material also can be doped with acceptor atoms that obtains electron from the valency band and leave behind positive charges called holes that also can carry current. Therefore, the energy levels of these donors and acceptors lie in the energy gap and creates a positive charge or electrons or holes. So, this is the schematic sketch showing the forbidden energy gap, showing acceptor levels is the typical distance above the top of the valency band, the donor levels on the typical distance below the bottom of the conduction band, and the deep trap levels nearer to the center of the gap. And the value of the thermal energy is indicated on the right, and this is the valency band and this is the conduction band. The cross hatching represents the marking of electrons, and you have 3 dotted lines in the band gap, and where you can say delta EA, this gap is delta EA and this gap is delta ED. That is, delta ED represents the energy gap at the donor level and delta EA represents the energy gap at the acceptor level. There are 3 dotted lines. So, the first dotted line near to the conduction band is called a donor level, and the next dotted line near to the acceptor level is called acceptor level. Between these two donor levels and acceptor level, there is a deep trap level. Therefore, a conductor is a material with full valency band and conduction band partly filled with delocalized conduction electrons. So, if the material has a delocalized conduction electrons and if it carries an electric current, such a material you call it as a conductor. Similarly, the positively charged metal ions at the lattice sites have given up their electrons to the conduction band, and it will constitute a background of positive charge for the delocalized electrons. Let us now turn our attention to the reciprocal space lattice. So, in the previous section, we discussed the structures of different types of crystals, and therefore, to treat the motion of conduction electrons, it is necessary to consider a different type of space, and this space you call it as your dual space or the reciprocal space, reciprocal dual space or reciprocal space. So, the other name for dual space is known as reciprocal space, and these spaces arises mainly in quantum mechanics, and therefore, there is a frequency f that is given by f is equal to omega by 2 pi, and k is equal to 2 pi by lambda, and therefore, when you substitute all this value in this equation, we get f is equal to k divided by 2 pi into nu. So, for a matter wave, the momentum is mass into velocity, that is p is equal to mu. Of an electron of mass m is given by p is equal to h divided by 2 pi k, where h is a Planck constant. Sometimes we can use h in place of h cross, where h cross is equal to h by 2 pi. So, when h cross is equal to h by 2 pi, we get p is equal to h cross k. So, therefore, for this simple case, the momentum is proportional to the wave vector k, and this wave vector k is inversely proportional to the wavelength, and we can define a reciprocal space or called a k space to describe the motion of electrons. For a rectangular direct lattice in 2 dimensions, say if there are lattice constant a and b, and the brilliant zone in this 2 dimension reciprocal lattice space 2 pi by a or 2 pi by b. Therefore, the extension to the 3 dimension is straightforward, and while discussing the reciprocal space lattice, it is very important to keep in mind that the reciprocal space kx in one dimension, kx is proportional to the momentum of the conduction electron in the x direction, and similarly ky is proportional to the momentum of the conduction electron in the y direction. So, this is the schematic sketch. The first diagram shows a unit cell in 2 dimensional with 2 coordinate space, where x and y coordinate space, and the second diagram shows the brilliant zone in reciprocal space for a rectangular Bravais lattice. So, the brilliant zone for x is 2 pi a, for y is 2 pi b, or for kx is 2 pi a and for ky is 2 pi b. So, this is for the first diagram refers to the unit cell in 2 dimensional, and the second diagram refers to the brilliant zone in a reciprocal space. So, let us now recapitulate what we have learned so far in this session. In this session, we discussed about face centered cubic nanoparticles, and we explained the theory of face centered cubic nanoparticles, and we also said a word about tetrahedrally bonded semiconductor structures. The best example for tetrahedrally bonded semiconductor structures are zinc blende structures, and we discussed about the lattice vibrations, how the lattice vibration arises in the lattice, and what are acoustic modes, what are phonons, and we discussed about the energy bands like insulators, semiconductors and conductors, and we discussed about reciprocal space. So, these are the topics we have covered so far. In order to have a better understanding, let me ask you some of the question. What is an insulator? What is a semiconductor? And what is a conductor? Define reciprocal space. Define brilliance zone. What is a phonon? What are lattice vibrations? So, these are the questions for the better understanding of this session. Thank you.